Okay, at the request of the owner of this tuner, and somewhat from my own stubbornness, not wanting to give up on this thing and let it beat me, I have decided to go on and continue on with doing this. Now, I have very gingerly removed the little glass dial indicator by removing the screws over here on the side and just leaving a couple of them in so that it will not completely come off, but getting enough of it to flex out so that I could remove this without touching any of this. We now have access to the dial, and you can see this just kind of pulls off very carefully, and these wires are so hair thin we have to be very careful, but you can actually swing this up very carefully and a couple of screws come out, and then we can access the bulbs in order to replace them. So that's what I'm going to do, and unfortunately I'm not going to do this on camera. I don't want to work around anything in my way while I'm doing this because it's very delicate work and I really don't want to damage anything. So I'm going to just kind of do that, and when we get things apart and back together there somewhat, I'll come back and show you our results. Okay, I have this thing turned around backwards so that you can see the two bulbs in there. And I don't know if the camera will pick it up, but you can just barely make out up here the top bulb and the bottom bulb. When I turn them on, it'll be very obvious that one of them's out. Here we go. You ready? And you can see the bottom one's lit, but this top one right here, not lit. And that's our problem. Now, again, I'm barely not going to move this very much, but I want to share this for the record in case any of you get one of these and ever gets to work on one. There's a piece of foam in here that's become very deteriorated. It's coming apart. It's basically glued between here and here, and that's what holds the locked and stereo, the tune and lock lights in. So that'll have to be, I'll have to come up with something for that. And then that has to be removed anyways because the bulb shield is actually soldered onto the board, and then the bulbs are actually soldered underneath. So all that's going to need cleaned off. And I'm going to do this all off camera, obviously. Don't worry about the front face of this. This glass is back painted from the rear. So touching the front, you're just touching the glass. If you touch the rear of this plate, you could damage that paint back there. So that does give me a little bit more confidence that if we fix this, I don't know if it's going to fix all of our problems, but at least it's going to create that 8-bit digital word to feed into the PLL circuit so it knows what frequency it's supposed to lock onto. That's essentially what this thing is doing with these, at least with these top, if you take a look, these patterns are broken up into different purposes. The bottom one actually is what tells you, each bottom notch tells you when you're over a station. So each one of those bottom ones. So each one of those is a station down here. So every 200 kilohertz, that's what this represents, every 200 kilohertz increment. Then the row above that, if you notice, it goes part way over and then it kind of stops right over here. You see it where it stops, and then it goes to this top row. This is what actually tells you, it's kind of what splits it between the bottom range of tuning and the top range of tuning. So in other words, the tuning ranges are not done in one complete sweep from 87.5 to 108.5 or whatever megahertz. It actually has two different ranges, and it will switch between those two ranges based on when you cross over that 97.5 megahertz, I think it is, crossover point. Don't quote me on that number. It's somewhere around there. Have to look it up. But anyways, wish me luck, because this is going to be very, very touchy, and I really don't want to damage anything. I'm just going to have to take forever and try not to damage it and carefully repair it. Okay, I'm just doing this here to document things for future reference. If you turn the board around, all of this had to be desoldered, and this whole assembly comes off as one piece, and the bulbs are actually kind of embedded in there, and I didn't know if I could get those out without cracking them by trying to pull on them, but you can see the little plastic grommets that they're mounted in. Now, of course, you're all thinking what I'm thinking right now, and that is, what do we do? Do we want to replace those with incandescent bulbs? Is there a reason that they have to be incandescent? Or can we replace them with LEDs? Well, I have a couple of concerns. Incandescent bulbs, if there's any kind of a pulsing DC going into there, or AC as it were, I don't know, that's going to be kind of canceled out by the filament of the bulb. And if you put an LED and there's the least tiny little bit of flicker, what is that going to do to that digital word going into the PLL? Is it going to cause the PLL not to lock? I don't know. I'm overthinking this, but I'm doing it because we get one shot at this, So I'm probably going to study the schematics a little bit more. And if I feel that it's a worthy risk to put an LED, we'll have to figure out the polarity first of all, and then we'll have to put them in there. Otherwise, I think I'll just go ahead and put another set of incandescents. Now, I do have some little grain of wheat bulbs that are 8 volt. I don't know if they're this tiny. These ones are just slightly smaller than the ones that you normally see in little dial indicators and things like that. But I do have some little tiny LEDs that will probably fit in there. I'll grab one. It's the wrong color, but I have them in the correct color. But see, I'm thinking something like this. If you look at this LED, it's very, very similar in size. See there? Almost identical. So I think I have some of those in white and in warm white, but again, I'm not sure what I'm going to do. But I'm going to look at the schematics now. And by the way, I want to thank Michael out there. You know who you are. You kind of read a little bit further ahead on the service manual, page 45. And it does actually give these, even though it shows this as an assembly, there's a little drawing of that on that page 45, and it actually describes each of the bulbs as an 8 volt 50 milliamp incandescent bulb. So thanks, Michael, for checking that out and reading a little bit ahead than I did. I basically just looked at the parts breakdown and it did not talk about that, so thanks for catching that. That's what I love about YouTube, and that's what I love about sharing this with you guys, because we all learn together and we all help each other out. Alright, let's see what we can get done with this. Okay, I have the bulbs installed, and I ended up going with LEDs, and they're warm white. They were perfect fit, and I just had to use a little 220 ohm dropping resistor, and that doesn't seem to be getting too warm. I'll have to keep my finger on it. That's actually, as tiny as that resistor is right there, that's a 1 watt resistor. I can always cut off the heat shrink if it ends up getting too warm. We'll check it. We'll just keep our eye on it. And I'm connected to one of the buffer transistors that comes off of this is the collector, which these are PNP transistors, so I'm on the collector, which is the output of that buffer amp, or these little buffer transistors. So when I run over one of the little dots that triggers this particular bit, my scope should go from a low to a high. So we'll go over to our oscilloscope, and I'm going to tune. I'm all the way over at 87.5 megahertz. I'm going to just tune through the dial, and there you go. And then if I keep tuning, you can see each time I cross over one of those lines, you can see. So my big fear was that possibly those little infrared, or those little sensors, light sensors in there, would not react to the light from the LED. But you know, because you never know if there was infrared or something, you know, that these little LEDs may not, you know, be on the same wavelength or something. But they're working fine. So now I'm going to go through the meticulous task of checking each and every bit to make sure they do toggle. So I'm just going to go down the line and check all those, and then we'll see what happens. I'm still not getting it to tune, and I think I said on the last video I didn't believe this was the only problem. This would just have been another problem. I think I still have a bad transistor. And I want to answer one of the comments that I had, because definitely what the commenter said was, you know, the viewer said made total perfect sense, and that is, you know, did you check the transistors? Well, I just wanted to give you a little heads up on that. I did, and the unfortunate thing is, if you remember from the last video, and if not, go check it out, this transistor right here was faulty. And however, I tried it on several different transistor testers, including what's supposed to be a very good transistor tester, this, you know, this Peak, plus the cheap eBay one, you know, different things. Every one of them said that the transistor was absolutely fine. You could ring it out with your multimeter set on diode check. It always checked good, but it would not work in circuit. That's the problem with these RF transistors. You can't always just test them, and if they test good, that does not mean that they're good. And this was a prime example. When you apply a high frequency to it, which is what this is, it's in an RF circuit, you're putting it under conditions that are different from what your little transistor checker is using. So you can't always trust a transistor checker. A transistor checker is good to test if it's shorted or opened. It's good to check the polarity of the you know, what leg is emitter, base, and collector. It can give you the static gain of the transistor, different little things like that, but it's not going to give you the performance. It's not going to show it under use. And so that doesn't guarantee, just because it checks good, that it is good. And case in point was this one here. That's the problem that I'm running into. You know, we may have another bad transistor in here, but you really have to do more than just pull out a transistor and test it. You really have to measure all of the signals and verify whether they're correct or not. And then once you eliminate all the other components as being suspect, you can kind of narrow it down to that transistor and then replace it and test it. Also, it's not practical to just replace transistors in RF circuitry, especially ones like this that use older technology. The modern replacements don't always work. So you start using new old stock transistors that are more expensive and more rare to find. Sometimes you can get a good crossover that's an identical match, but you have to find that by comparing specs and things. It's not so easy. So yeah, we do check the transistors, but that's not always telling you the whole story. I guess that's the answer to that question. So I'm going to go through and check all these, make sure they're toggling properly. Once they are, we're going to go back and we're going to focus again on why I can't get my 122.8 megahertz and why I can't get that portion of the quadrupler circuit to oscillate. Okay, another progress update. So I now have 30.7 megahertz here, and I'm actually using the spectrum analyzer to check it. It's just too difficult. The oscilloscope just isn't sensitive enough, which when you work with our RF equipment, you really can't use a scope on the front end. You know, some of this stuff, it's so sensitive to all that. But T1 is tunable, and I have it peaked at 30.7 megahertz. I'm getting everything in here that I want now. However, I'm not getting an output. I have a goes into, but I don't have the goes out. I am not getting my 122 megahertz. I am getting something. and I'll show you on the spectrum analyzer what I am getting. Let me hook it up real quick. And if you look over there, let me zoom you in a little bit better. You can see I'm getting, it's right at 103.12 megahertz. So instead of 122.8, it's 103 megahertz. And it will not peak. In other words, when I adjust this slug right here, which is T2, which is right here, it has absolutely no effect. And of course it won't have any effect if this transformer is designed for 122.8 megahertz and you're only putting 103 megahertz into it, it'll never peak no matter where you adjust it. So something in here has to be causing our problem. Of course, it can't be anything over on this end because you have this capacitor kind of blocking all that. And you know, if I check on this side, of course, even the high impedance input of the spectrum analyzer could affect this somewhat, I'm sure. But I am pretty confident that that's our problem, is right in here right now. So what could it be? Could it be something with this? I mean, you're dealing with such tiny values. Look at this. It is a 2 picofarad capacitor. If that capacitor, and you can see it's an external capacitor that's shunting across this coil here. Normally that would be inside, kind of like this one over here. If you look at it, it's got the capacitor built into the can there, right into the transformer. This one has an external one, which happens to be this little yellow one right here, this one with the yellow paint on it. That's your 2 picofarad capacitor. And it's right next to the... Like I said, this machine, I don't know, man, the way it's designed. Definitely a challenge to work on. The other problem is you can't access this board from the bottom. So every time I have to do something to it, I have to take the 4 mounting screws out, flip the board up, and then all the wires are attached at this side, so you can't bend them too much or they'll break because they'll get brittle. And each of the 4 screws is a ground plane, and they each need to be screwed down to properly ground this. This doesn't have proper grounding if you don't screw it down. So yeah, there is a ground wire on here, but the ground bus doesn't really, I don't know that it connects all the way to all 4 corners. It might, but I'm not taking chances. I screw this down every time. So it's very tedious to remove or replace any component. Now I did, you know, check the transistor to make sure there wasn't something strange going on with it. This is a new one. It works just the same as the old one, so I could put the old one back in. Again, the quadrupler circuit is what's not working. So it's the tripler is working. We're getting our right on, bang on 30.7 megahertz, and we can peak it. But this quadrupler circuit right here is not working, and it has something to do with this section here. So that's where I am right now. I'm not sure what it's going to turn out to be, but just going to have to think it through a little bit more. Again, you know, little by little, we're figuring this out, but boy, is this complicated. All right, folks, let's repeat what I just said, because the last one I did was with the microphone turned off. Take 2. Gotta love this. So what I'm doing is I'm skipping ahead a little bit. To catch you up with where we're at, using the frequency or the spectrum analyzer and using a DC block and a high impedance adapter and everything, I was able to put the spectrum analyzer into that board, to that synthesizer board, and 100% verify that the 30.7 megahertz oscillator is working. And I was able to peak out T1 and T2 right here, kind of like what we were looking at, to get the 122.8 megahertz. Here's the catch. That 122.8 megahertz had a lot of harmonics on it, as I probably had expected, because there's really no filtration to filter them out. So there was a lot of harmonics. The harmonics were really wreaking havoc on my frequency counter. So really, without the spectrum analyzer, you just couldn't see what was going on. The other thing was I was able to massively increase the amplitude of the 30.7 megahertz, which massively increased the amplitude of the 122.8 megahertz. But even though it was, and then the other one, between the two, I was able to kind of neutralize a little bit of the harmonics, and I was able to at least get 122.8 megahertz dead on signal at TP20, that little test point that we were looking at right here. And the thing is, though, to me, the amplitude looked way, way, way low. It's much lower there than it is at the 30 megahertz and than it is at the at the 10.232 or 2325 megahertz. The other thing I noticed was when we get to this one where you plug the VCO in cable back together, as soon as I turn it there and I align the dial pointer to 87.5, this adjustment here, which is that square wave, completely disappears. If I unplug the VCO coax, I get my square wave. I plug it back in, it swamps right out. So the reason that we're doing what we're doing now is I'm going to move ahead a little bit from the synthesizer and do the next adjustment, which is the local oscillator, which is your VCO. So it's kind of complicated the way they want us to do this. What they're saying is they want you to disconnect from the FM front end, where your tuning gang and everything is. They want you to disconnect pins 6 and 8. You actually unwire wrap them. And then they want you to take pin 10 of the power supply board, which is your 13 volts, and jumper it right onto pin 6. Then they want you to take pin 6, which is your 12.4 volt power supply on your power supply board, and build this little makeshift voltage circuit, voltage adjustment, and then wire that into pin 8 where you disconnected the wire. Then they want you to connect a voltmeter, a DC voltmeter, from pin 7 to pin 8. And they want you to set it very accurately for 8 volts and then adjust the coil for 97.5. Then they want you to adjust it to 17 volts and adjust the capacitor, TC6, okay, and those are on your tuning board, for 110.5. So my concern was, what if these are wrong? If they're wrong, maybe that's why when I plug the VCO cable in, it would jump out. So that's why we're here right now, and that's why we're no longer on the other side of that board, okay? So here it is. You can see the power supply board. You can see this is your 13 volts and this is your 12.4 volts. The 13 volts jumpers right over to that pin 6 as indicated. Pin 5 is your frequency counter, which is right here. I'll zoom you in a little more. Then pin 7, you can see the black probe right here. That's this black wire right here. That's going to the negative lead of my voltmeter. And then I have my pin 6, or pin 0.8, which is all the way over here, is this yellow wire, and it goes down to this little cobbled together mess. I had a 20K pot. They want a 15K pot. So I took a 20K and I shunted this 51K between the wiper and the bottom part, the ground lead of the pot, and turned all the way up. It's a little bit over 14K instead of 15K, so it works. Then a 1.8K, and this is your limiting resistor. So that's coming out of that. Then you have your meter and the yellow lead going up to pin 8, and the red lead there goes up to the meter. And you set your meter so that you see approximately, well, not approximately, exactly 8 volts. So you can see how close I have it right now, 7.99 volts. And let's see here. Am I going the right way? Yeah. No, wrong way. Yeah. Okay. So you just adjust that pot till you get right on 8 volts, and that's about as close to 8 volts as you're going to get. I mean, we're messing with, you know, a millivolt or two. There. Good enough. Anyhow, there's your 8 volts. And you can see we're right on 97.5 megahertz. There it is. So now that's where I'm at. My next thing is to adjust the pot now till I get 17 volts, and we should see 110.5 megahertz. So let me do that and I'll be right back. Okay, here's our 17 volts, and as you can see, not very happy with that, and it's bouncing around. I'm seeing frequencies anywhere, and you can see it's going up to 117, 118, it'll drop down. I'm never getting my 110. And this is actually a trimmer capacitor, TC6. So the capacitor might be a little bit flaky, or just might be a little, you know, have some crud on it or something. So we're going to try to adjust that and see if we can get our 110 megahertz. The other one, I did adjust that L6 coil, just barely touched it, and it brought it right in, and it was barely out. I mean, it was 97.56 or something, and you know, I really had to fiddle with it to get it 97.0 because it's so touchy. So I think it was on. This one, however, as you can see, is not. We are not getting 110.5 megahertz. So I'm going to adjust that, and I'll be right back, and we'll see what we get. Okay, I now have my adjuster right on the trimmer pot, or the trimmer capacitor, and I got it pretty close. But the problem I'm running into is it's not holding very well. As you can see, it's dropping down as soon as and it's very hard to keep it where it needs to be. And you can see just barely touching it, it drops and goes up and down and all over the place. So, and you can see as soon as I let my finger take the tweaker off of the adjuster, it goes crazy. And that's about as close as I can get it right now. And you can see just sitting here, it jumps and goes all over the place. And you can see I'm not doing anything, I'm just standing here, and it goes in and out, in and out, in and out. So either we have a bad trimmer capacitor, which is entirely possible, or we have a bad component in our local oscillator. So now our next challenge is to figure out why this is doing what it's doing. Now the 97.5, it was right on. We didn't have any problems with that. But with this, it's jumping all over the place. And my voltage is dead on. It's not moving. I'm like watching it right now, watching the voltmeter. It's not moving at all. It's rock solid. So it's definitely something either in that trimmer cap or something like that. But there's definitely a problem here, and that's the problem I'm running into with this tuner. It just has multiple issues with it. I think because of its age, everything is so precise, and if anything drifts the teeniest little bit, this is what you end up having, is stuff like this. Anything changes, it just goes crazy. The other problem is we don't know if, I don't think recapping it right now is going to fix it, but we have all original capacitors, all original components. We don't know if any of those are acting up either. Do you want to invest the time and money, though, into doing a full recap on something that has other major problems that aren't going to be fixed? You've just wasted all those components and all that time and money and whatever. Very hard call on something like this. So little by little we are moving along, but definitely it's fighting us every step of the way. Well, here we go again. So I'm looking at the schematic for the front end board, and the first thing I notice is here's pin 5, and pin 5 is obviously where we're hooking up our spectrum, or our frequency counter. And you can see again more modifications drawn on here. And again, this is factory. This is the one I downloaded from Hi-Fi Engine that all the rest of you have looked at from my first video. And you can see where they've actually taken this 320 or 330 ohm resistor and jumpered it out, cut this wire off right here. You can see here they cut that track there. It goes into the JFET, comes out of the JFET. You have this little 100 ohm resistor that was originally tied. Instead of having this go directly to ground, they're floating it with a 100 ohm resistor. Then it goes into the output here of your, with your decoupling capacitor. The other thing is, if you recall, we were connecting to pin 8 is where your reference signal comes in. Here's your varactor diode, your varicap diode, and this is actually, it's a diode that acts like a capacitor, and the capacitance of this changes with the amount of voltage you apply across it. So if you look, this is your low side here. This is the ground where they're actually having you check it. That's where we're putting the negative probe of the meter. Positive probe we're going here. So by applying a voltage between, it looks like here and here, we're applying 2 voltages. This is where you're putting your 13 volts, and this is where you're putting your variable voltage. And then they're changing this from a 1K resistor to a 47 ohm resistor. So my question is, this instability that we're seeing right now, the other thing is, instead of Q6, which is this up here, I think, let's look. Yeah, Q6, instead of being a 2SK61 JFET, it's a 2SK, I don't know what that says, 10W. I can't tell because they wrote over top of that little arrow, and it's very, very hard to make out. Even though it's very clearly printed, the way they drew it on there, and it's handwritten. But obviously, they replaced this with a different JFET. Obviously, there was a reason for that. Now, my question is, is something broken in here? Or are we seeing a representation of the problems that they were having with these, and this is the modification that should be done? Do I do it, or do I not do it? Without any kind of notes on this, really hard to know what to do. But you can see every single turn that I go on, I hit a dead end with something, and I have to reverse engineer it to figure it out. Everything kind of works, but doesn't seem to work properly. So that's our next challenge. And again, once I get this functioning, I have to go back to that synthesizer board because we're still not getting not a lock, but an on-channel light. I believe, but I'm not 100% sure, there's 3 lights on that tuning dial. One is stereo, one is locked, and those ones we're never going to get until we tune in a station. But the one below it is just a little LED that sits by itself. And that LED, I believe, is supposed to come in every time you cross one of those 200 kilohertz channels. So every 200 kilohertz from 87.5 up to 108.5, it's every 200 kilohertz when you cross over that little dot, that little encoder dot, it's supposed to tell you you're over top of a channel, and that's where it can lock on. That's how it locks the PLL. That's kind of like an on and off. If it's not over top of one of those and you don't get a trigger, the PLL is not even going to be told to lock on what the digital word is. So I'm never seeing that either. So once again, I have to see if I can find what it does when it is working. So there we go. I don't know. I'm probably going to edit this video just and post what I have to at least let you guys know that I'm still working on it, and that I haven't given up on it yet. But I will tell you, it definitely will try someone's patience. This thing here is just I think the bigger issue than this being so different and complicated is the fact that there's so few people that have actually serviced these that can give you a definitive answer of what something's supposed to do. I mean, yeah, you can look at a schematic and say this is how this circuit works, but when you put all the pieces together in the arrangement that they're in, getting somebody to tell you the big picture, that's a different story. So really, I'm kind of in uncharted waters is how I feel on this. And definitely a learning experience, and definitely something I'll never forget if I do get it working. And even if I don't get it working, I'll never forget. So that's where we are. So a little observation here before we close things out, because we're winding this up. You can see right now it's 100 and it's just going all over the place. But every once in a while, if you sit here and watch long enough, it'll drop to 110.5 megahertz where I set it. And it'll be just fine. And then after a couple seconds, it'll go crazy like this again. So whatever it is, I'm almost wondering if possibly it is one of those JFETs, or possibly that Varactor Varicap diode is failing. Now I have a couple of spare, I have some spare Varactor diodes in stock, but of course we would have to look this one up and see whatever its properties are, because they're all different. The range of capacitance versus voltage and everything, you can't just put a random one in there. So I'm almost thinking something like that is causing our problems right now. So I don't know. We'll just have to keep troubleshooting, I guess.